My name is Leah Peterson, and I'm the Adult Programs Coordinator here at the Bell Museum of Natural History. And for those of you who maybe have attended a Café Scientifique in the past couple of years, you will know, oh, hello, thanks for coming. You will know that many of the faculty from the Astrophysics department here have been guests and or hopefully will be future guests at Café Scientifique, including our speaker tonight, Clem Pryke. But it's not my job to introduce him. My job is to just let you know, first of all, that we are, as you can tell, taping and video recording tonight in the hopes of putting together some kind of archived video that you'll be able to access in the future. The fate of that is yet unknown, but we'll be able to notify you through our websites and whatnot as we put something together. Because of that, we ask that you certainly make sure that your cell phones are off so that we don't have ringers getting picked up on the video. I had to remind myself of that just a few moments ago. So also, we'll have a question and answer after our talk tonight, and we'll have a mic like this with a moderator going around in the audience. So it'll be a hands raised kind of question and answer period, and we'll try to get your voice onto the microphone, and who knows, maybe you'll end up having a little moment of stardom in the video as well if your voice is nice and clear. So without further ado, because we have so much great stuff to get to tonight, I would like to introduce to you the director of the Minnesota Institute for Astrophysics. This is the inaugural MIfA lecture here at the Bell Museum, and Evan Skillman will be able to tell you more about that. But as the partners here at the Bell Museum for the Minnesota Institute for Astrophysics, we're very pleased and excited to be working with them on bringing this lecture to you tonight and hopefully more in the future. So why don't I pass the mic over to Evan Skillman, and he will tell you more about what's going on tonight. Thank you so much.
Well, thank you so much, Lee. It's just great to be able to work with you and all your colleagues at the Bell to be able to present this. And as she said, this is our first lecture in a lecture series. I have a very short story about that. I don't know, how many of you were here 2 years ago for Carlos Kaufmanis' lecture on how I killed Pluto and why it had it coming? Can I see my hands? Okay, so it was a fantastic lecture, and I was in the audience, and he told a tremendous story. And it struck me at the time that within our institute here at the University of Minnesota, we have so many wonderful stories that we're not sharing. And so I wanted to share those stories and have asked my colleagues to put together this Minnesota Institute for Astrophysics public lecture series. And so this is the first. And as you'll see, this is going to be a great series. The overview for tonight, we'll have Clem will give his talk. We'll have plenty of time for questions afterwards. And then when you all had your questions answered, you can go back through there, and in the Bell Museum is this exhibit, Eyes on the Universe, and we have plenty of time. That exhibit will be open and free to you to go peruse until 9 o'clock this evening, okay? So after the lecture, question and answers, and after the question and answers, then you can go down and look at the Eyes on the Universe exhibit, okay? The final thing I have to do tonight is to introduce Clem. Clem has been at the University of Minnesota for 4 years, and as you will see, we're extremely proud to have him as a colleague. We're very excited. It's no accident that we chose him for the first lecture. You're just going to enjoy this so much. And so without further ado, I'm going to hand over to Clem.
Well, thank you very much, Evan. So I'm going to dim the lights a little here. So you will have seen the video that was playing as you came in, and that was our telescope. I'm going to play it again, I think, because to explain what you're seeing here. Turn the sound down. So what you're seeing here is the telescope, one of our telescopes down at the South Pole, observing in the deep night. So as I will come back to a little later, at the South Pole in Antarctica, there's one day-night cycle per year, right? You're on the Earth's rotational axis. So that means that the sun spirals around, goes up, and then spirals around and goes below the horizon and stays down for 6 months. And about 5 months of complete darkness. And so this is the telescope doing its observations in the deep night. And you can see it's massively speeded up, of course. So this is a great big steel platform that carries the telescopes, and it's scanning backwards and forwards, observing the sky. very speeded up, so these scans take about a minute, and you're seeing them in a second or so. You can see the arc of the Milky Way in the night sky above, and the Earth rotating, right? So if you're at the South Pole, the night sky just goes around and around above the zenith, above the straight-up direction. You can see the Milky Way. You can see some shooting stars going across. You can see satellites going across. And you can also see the aurora coming and going, the southern lights. Actually, they're just reached a dim point as I mentioned them. But our telescope is completely insensitive to all of those things, right? It's looking way, way further out into the cosmos, and I will explain what it's all about. So here's a different picture. It's actually a different telescope, but very similar. This is the main one that I'm going to be talking about this evening, the Bicep2 Telescope. And it's sitting inside this bowl-shaped ground screen, the objective of which is to protect it from radiation coming from the ground, because we want it only to see radiation coming from the sky, from the cosmos. You can see the sunset occurring in the distance there, a very emotional event for those foolish enough to witness it, right? Because if you see it, in fact, if you miss the last plane, which is considerably before sunset, then you're stuck there through the long night, waiting for the sun to come back so you can leave, so the planes can fly again. So projected onto the sky here is a kind of artist's impression of the polarized pattern that we measure with these telescopes, the polarization of the so-called cosmic microwave background. I'm going to explain much more about what that is. So, okay, so now let's take a real step back closer to home, right? So I like to start these lectures, it's just a very general lecture, so let's just start with a really basic fact. Our sun is just a star. It's just an ordinary star, right? So we find ourselves on this rock that we call the Earth in orbit around a star, and we think it's very special, right? Because it's the one that gives us life, that, supports our entire solar system. But it's just a very ordinary star. This is how it was just 48 hours ago. There's a spacecraft which constantly monitors our sun, the SOHO spacecraft. It's taken in a funny wavelength band, so you can see all the structure, and it looks very dramatic. But it's just an ordinary star, okay? So, as you all know, probably many stars make up a galaxy. So about 1 trillion stars make up a big galaxy. This is a nearby galaxy, but we think it's pretty similar to our own. If we were outside, if we could look outside of our galaxy and look back in, we would see something pretty similar to this, and we would be a completely insignificant star, kind of 2/3 of the way out in some suburb of the galaxy. So many stars make a galaxy, but then there are many, many, many galaxies, right? So this is the Hubble Ultra Deep Field. So they took the most powerful telescope that mankind has created, and they pointed it at a blank patch of sky, right? They deliberately selected a patch of sky where there was nothing interesting, right? And then you look, accumulate data for many weeks, and gradually, with this incredibly powerful telescope, these tiny little smudges come into focus. And what these are is these are incredibly distant galaxies, actually looking far back in time, right? And these are just shows just the vast number of galaxies which make up our cosmos, right? So the universe is absolutely vast, and we don't appear to be in the least bit special, right? So it's a very humbling thing. It's to look out into the cosmos and just see its vastness, its complexity, and our incredible averageness in this universe. Yeah. All right, so just a few words about what light is, because all of the information that we have about the universe we get through the light that it sends to us. That's still true. So thus far, at least, everything we know comes from light. So light is an electromagnetic wave. So this is a kind of representation of an electromagnetic wave. Imagine this thing. It's this rippling thing, and it's moving incredibly fast in this direction off the screen to the right. Now, it's microscopic, right? Like a single ray of light, as it were. It's a tiny, tiny little thing. You can think of it as kind of a little wave packet, a little wave train that's zipping along. Now, it moves incredibly fast, but not at infinite speed, right? It takes 8 minutes for light to get from the sun to the Earth. If the sun stopped shining instantaneously, we wouldn't know about it for 8 minutes, because that's how long the light takes to get to us. The characteristic thing about any given ray of light is its so-called wavelength, the difference from one peak in the electric field oscillation to the next. And that is AKA the color, right? The wavelength, the color, it's the same thing. Now, another thing that's key to tonight's talk is to appreciate that visible light and radio waves are just the same thing, right? It's just that radio waves have a much longer wavelength, right? Light has a wavelength of, about 300 to 600 nanometers, billionths of a meter, right? Whereas radio waves can have wavelengths up to the meter scale and longer. But they're just the same thing. It's just one is a rescaling of the other, right? One is just a rescaling of the other. All right, so if you had three stars that were simultaneously emitting a ray of light of the same natural wavelength, right? Had they been stationary, we would have gotten the same color of light out of them for the ray that they're naturally emitting. Imagine we're an observer over here on the right of the screen. Now further imagine one of the stars is stationary, and it's giving this nice yellow ray of light. One of the stars is moving towards us, and the wave train gets compacted. It gets squished, and that makes the ray of light have a shorter wavelength and makes it bluer. If the star were moving away, that wave train gets stretched, and you get a redder ray of light coming out, right? So this is the classical Doppler effect, where the wavelength that you get depends on the relative motion of the thing that's doing the emitting and the observer, okay? So in the 1920s, about 90 years ago, there was this guy called Edwin Hubble, many of you will have heard about, a very famous astronomer, and he was using a large telescope that had just been constructed at that time on the Mount Wilson Observatory in Los Angeles. And this is a very funny picture, right? Because here he is looking through his telescope, you know. Now, it was kind of a pose at the time even to have him look like he was looking through a telescope, because around this time, astronomy was shifting from actually looking through telescopes with eyes to using photographic plates, right? So all serious work was being done with photographic plates. Now, apparently this is an even more ridiculous picture because the telescope right now is pointed at the horizon, right? It's not even pointed at the sky. And this is a total posed publicity shot, right? So he was quite a man for self-promotion. So, you know, even 100 years ago, scientists were already interested in their PR and their public image. Anyway, what he did, and he was a very brilliant man, he used this massive telescope that had recently been built to look at rays of light from distant galaxies and look at how the light from those galaxies had either been stretched or compressed, right? He was measuring the Doppler shift, apparently, of the light from those distant galaxies. And he could also get, by independent means, a handle on the distance to the galaxy. So this is the plot that he drew, the famous Hubble diagram. On the x-axis, you've got the distance to the galaxy increasing. On the y-axis, you've got the apparent recessional velocity, the apparent the red shifting of the light, the amount the light was being stretched from that galaxy. And he converted that into a velocity, right? Because you can easily make a conversion from the stretching that you've got to the apparent recessional velocity of the thing that's doing the emitting. Each point was a galaxy. Each point on this diagram is a galaxy. And he found that the further away a galaxy is, the faster it appears to be moving away from us. Okay? And this is a very, very perplexing finding. I suppose he was expecting to find some of them are moving towards us, some of them are moving away. On average, you know, everything's just squirreling around like fish in a fish tank, right? But instead, he got this very bizarre result. The further away, the faster it appears to be moving away. So what are we? The most unpopular place in the universe, right? Did a massive explosion go off at our location at some time in the past, and we're just seeing the debris fragments flying out? If that were the case, then we would be a very special place in the universe. But yet, when we look at our local universe, we look at the more distant universe, we don't look special in the least, as I already emphasized. So this was a very strange observation. Now, what was rapidly realized is that the simplest explanation for this, and I put an exclamation point on that because, you know, it's not simple at all, it's completely mind-bending. But the simplest explanation seemed to be that the fabric of space itself is expanding, right? So this cartoon shows an analogy. Now, let's imagine a two-dimensional universe which is on the surface of a three-dimensional object, like a balloon, right? Now, you can extend the analogy, and you can say that we're a three-dimensional universe embedded in some four-dimensional space, right? Now, don't try and picture a four-dimensional space, because you can't, right? But we can picture three dimensions and two dimensions. So let's imagine that the space is the surface of the balloon. The coins stuck to the balloon are galaxies, and the balloon is inflating, right? It's getting bigger. And so if I'm sitting on any given galaxy and I look out at the surrounding galaxies, they all appear to be moving away from me. Furthermore, the ones that are more distant appear to be moving away faster because there's more centimeters of balloon between us and them. And so as the whole thing scales up, they look like they're moving away faster. And so from wherever you look, the more distant objects appear to be receding faster, which is exactly what we've got. There's actually a nice fine point to this analogy, which is that the galaxies are represented by coins stuck on the balloon. And that's reflective of the real situation. What's expanding is the intergalactic space, right? The space here in our galaxy is not expanding. The moon's not getting further away, right? It's the intergalactic space that's expanding, and that's a fine point, but it often gets asked, is the galaxy expanding? It's not. Okay, so in this scenario, the reason that the light is redshifted, is stretched from these more distant galaxies, is not because anything's moving in space, right? Space itself is expanding. And what's happening is that rays of light, which have some initial wavelength, and in this animation, imagine the yellow dots, that's the fabric of space, right? We are the white one in the middle, but you could just recenter the thing on any of them and it would appear the same. Now let's imagine we're the stationary one in the middle, apparently stationary one in the middle. And then we've got light that's coming to us from two different two galaxies, one of which is twice as far away as the other, right? Now this one spits out an initially blue ray of light, and as it's en route to us, swimming against the tide, as it were, of the expanding space, it's getting stretched because it's riding on the fabric of space, and the fabric of space is stretching. The one that, and we've timed things so that they arrive simultaneously, right? So the one that comes from further away takes twice as long to get here. The one that's coming from nearby is emitted much later, and it arrives at the same time. And whilst it's been in flight, space has stretched less, so when it gets here, it's still bluer, right? So they both start off blue. The one that comes from further away ends up redder than the one that comes from closer by, right? So the important point to note is that as we're looking out, we're looking back in time, and the most redshifted light is the light that comes from the longest ago, okay? So I call this the cosmological Doppler shift to make it very distinct from the regular Doppler shift. All right, so shortly before Hubble was making his observations, Albert Einstein was cooking up the general theory of, well, first of all, the special theory of relativity, and then the general theory of relativity. People often think it's the other way around, right? The special one must be better. But actually, it means special as in special case. General as in general case came afterwards and is the more profound theory, the more all-embracing theory. I also like to show pictures of scientists around the age when they actually did the work that they're famous for. Because sadly, even for me, scientists do their important work when they're young, right? Particularly theorists, right? It's generally true, actually. If you look at the history of science, most of the really important stuff comes from guys when they're young. And he went on, of course, so I like to show him here as a dapper young man, right, in 1912, when he was doing the stuff that made him famous. Later on, he grew all this crazy white hair, and, that's the public image of Einstein. But by that time, he was not actually doing stuff that was really cutting edge anymore. He'd actually kind of gone off the rails a bit and was in an area which we now believe to be kind of a dead end. So in 1915, he'd produced this theory of general relativity. And general relativity is the bedrock on which cosmological theory is built, right? It is a theory in which space and time are combined into this thing called space-time. It can be curved. Space can be curved, right? Again, a mind-boggling concept, which we can only visualize by projecting it into two dimensions, right? So if you imagine this sheet is a two-dimensional surface in a three-dimensional higher, there's a third higher dimension, then it can be curved, right? And in fact, the space around our own sun is slightly curved. If we look at the light from a background star as it passes behind the sun, we can see very small deflections in the direction of the light as it goes past the sun, kind of like a ball rolling across this curved surface, right? If you roll a ball fast across the surface, you kind of aim it towards the center, not right at the center, but close, then it will curve, it will be deflected as it goes past the depression, the curvature near to the star. Now, what Einstein realized when he was devising this theory was that it had profound implications for cosmology, for the whole universe. And he also realized that it was intrinsically unstable. any universe in this theory would either tend to expand or contract. Static was a very special case, and in fact, the natural equation didn't favor it, didn't favor a static universe. So he put in a fudge factor. This lambda here is a fudge factor which exists in the equation. It's like an ugliness introduced into a very beautiful theory, entirely designed to force a static universe. Because at that time, everybody knew the universe was static, right? The ancient Greeks had known it was static. You know, the medieval philosophers had known that it was static. The Christian church knew that it was static, right? There was no real reason to believe this. It was just a kind of article of faith. So he fixed his equation to make it static. And then later, when he heard about Hubble's observations just kind of 10 years later, he called this his biggest blunder. And of course, they took it out. Now, it's now actually, in present-day cosmology, it's back again. But that is a different story, not tonight's story. All right, so modern cosmology in a nutshell, right? The universe is expanding. It was realized pretty rapidly that if it was expanding, then at some time in the past, it must have been denser and hotter, right? And if you wound the clock back without limit, it must have been very dense and very hot. Gamow and Hermann, Alpha Gamow and Hermann in the 1940s realized that once the density of the universe must have been as dense as an atomic nucleus. And they had now rather naive theories that they called primeval atom theories. But basically, they were on the right track. The universe was once very hot and very dense. It was realized that you ought to still be able to see the glow from that time. So we all know that hot objects glow, right? If you heat something up in a fire, heat up a bar of iron in a fire, it glows, right? The incandescent lamp filament in a regular domestic light bulb glows. So it was realized that that hot, dense universe, early universe, would have been glowing. And furthermore, that glow ought to still be there, right? But heavily redshifted, because the universe has expanded by a large factor since that time. So that light, which started off as like, you know, the blinding white light of a hot iron bar, would have been redshifted all the way down into the microwave region. So microwaves are kind of somewhere between visible light and radio waves, right? Microwave, we're talking about frequencies of gigahertz to hundreds of gigahertz. Maybe your cell phone is a device that uses microwaves at the few gigahertz range. So it was realized that there ought to be this microwave background, this cosmic microwave background glow. People at Princeton University had built a special experiment to go looking for it, but actually they were beaten to the punch by some guys down the road at Bell Labs, Wilson and Penzias, who detected it using this very strange-looking horn antenna in the background that had been built for communications engineering, actually. So they got the Nobel Prize for that. And it was rapidly accepted that the universe did have this hot, dense early phase. So here we find ourselves at about 14 billion years after the beginning in this intensely beautiful, highly structured present-day universe of galaxies and stars and all of the exotica that are in it. As we look back in time in that Hubble Space Telescope photograph that I showed you, we're looking back to the very early phases of galaxy formation at around a couple of 100 million years. And we can actually see those as little smudges, right? We can see those early proto-galaxies at around about 200 million years when the first stars were lighting up. Now, when we look at the cosmic microwave background, we're looking back way beyond that. We're looking back to about 380,000 years after the beginning. Okay? And we've studied the hell out of this cosmic microwave background, and it's going to be the subject of the remainder of my talk. I'm going to come back to inflation. So inflation is an idea of what happened in a tiny fraction of a second after the beginning. But first of all, this microwave background, what can we learn from it? So the cosmic microwave background presents us, when we point sensitive microwave frequency telescopes at the sky, we can see the whole sky is glowing, right? Not just, you know, the glow from the Earth's atmosphere. That's very annoying. We have to go to a special place to get away from that, as I'll come back to. But the whole sky is glowing, and it's glowing with almost equal brightness in all directions. We can map out the whole sky by waiting for the Earth to turn, or by putting telescopes at different latitudes, or by putting telescopes in space. This map is a map of the real microwave background sky made by a space telescope, by a space mission. And what they've done is they've taken the data that they collected over the whole of the so-called celestial sphere, right, the whole sky that we're looking out at, and it's been projected here for display on the surface of a sphere. So you have to imagine we're at the middle looking out at this surface. And it has almost equal brightness in all directions, but there are some little ripples and dimples in that brightness of glow. And they have been measured very well now. And what they represent is very small variations in the brightness, in the density, in the temperature of the universe as it was at 380,000 years. Now, of course, at that time, the whole universe was glowing, and it went through a phase transition. It went from being a plasma, like the plasma inside a fluorescent lamp, to being neutral gas, like the air in this room. Now, a plasma is constantly rescattering the light, right? Scrambling its direction. But a neutral gas is transparent. And so at about 380,000 years, those rays of light, of hot object light, went from rattling around to suddenly going in straight lines, going unimpeded in straight lines. And so the ones that we see when we look at the sky are the ones that just happen to set off, heading in the direction where the Earth would later form, would later be 14 billion years later, so that we could receive them with our telescopes. And so what we get when we map out the microwave background sky is a density sample of the structure on a shell, on a spherical shell, cut through that infant universe. Okay? Now, you know, the universe, of course, had structure elsewhere, and if we were over here, we would be observing light from a different shell, right? So what we get is a core sample, a two-dimensional map of this shell cut through the universe at that time. And that's been studied in great detail. Now, what we do in order to study that structure, so when we map out the structure, it's just this kind of blobby pattern, right? But so in order to do something quantitative with that, we plot it on a plot of this kind, right? I'm going to try and explain what this plot is. So on the x-axis, we have the size of the blobs, right? So you can see when you look at this, there are some big blobs, you know, like this one or this one, and then there are small ones, little ones. And so what we do, essentially, is have the computer count the number of blobs of each given size. Now, in the way that we plot the data, the smaller ones are actually over here on the right, and the larger ones over here on the left. And the y-axis is just representing the amount of blobs, right? Less being further down this way, and more being further up. And so you can see that, so this is essentially just a histogram of the number of blobs of given size. Now, the data points are these colored points coming from various different experiments, and there is a theory curve behind here, right? So a lot of the time what scientists do is they take data, and then they have a theoretical model, and then you adjust the parameters of the theoretical model until it fits the data, and so you discover the parameters, you know, of the universe, of the real universe in this case. And there is a theory curve behind there, but it fits the data so well you can hardly see it. There's this beautiful series of so-called acoustic peaks. I'm not going to go too far into explaining why or what they are, but suffice it to say that using this confrontation of data and theory, you can measure the parameters of the universe, how old it is, and how much stuff of the various kinds it's got in it, with very high precision. So we have the current situation in cosmology. It's both triumphant and embarrassing, right? Because we've measured the amounts of stuff in the universe, and we find that the stuff, the ordinary atoms, the so-called baryonic matter, just atoms, ordinary stuff, like we're made of, like the Earth is made of, like the sun is made of, they only represent about 4% of the total amount of stuff in the universe. About another 20-odd%, 20 to 30% is the cold dark matter. Now, this is stuff that we already knew about from other means. We'd already kind of guessed at its existence from other means. The CMB has really tied it down and really measured exactly how much. And this stuff we believe to be like some kind of particle that we can't easily measure. But it's right here in this room passing through your body right now, right? That's also the subject for another lecture, but it's not tonight's. And the other 73% of the universe is dark energy, which is something even more mysterious. This is an energy density of empty space itself. So if you had a vacuum, if you had like a cubic meter of absolutely nothing, you got all of the ordinary matter out of it, you got all of the dark matter out of it, although we have no way of doing that, but if you could, then you would still have some net energy density. You'd still have some net energy in there. And that's a strange thing. It's something that physical theory allows, and it seems to be the case. And so a large part of the total energy budget content of the universe is made up of this dark energy. Now, it's a beautiful theory. It fits the CMB data beautifully. It fits all sorts of other data very well. It's taken as kind of canonical law. The cosmologists argue about measuring these numbers to finer and finer accuracy, but they don't question the basic model. But it's also a very strange model because it implies that the universe is going to expand, not just as it's expanding now, but it's going to speed up. The expansion is going to speed up, and it's going to speed up, and the universe is going to undergo some kind of big rip. So this is a diagram showing the time relative to the present. Here we are in the present day at 0, going back in time, negative times, going forward in time, positive times. And this is the scale factor of the universe, the so-called, I call it the stretch factor, right? And so let's just define that to be 1 right now. And we can ask, what was it in the past, and what will it be in the future? And the observations say that we live on this red line. So not only the universe is kind of expanding at a linear rate right now, but in the future, the expansion is going to accelerate and accelerate more and more. And in the distant future, if we were looking with our telescopes 20 billion years from now, we would see the galaxies around us much further away and rushing away much faster. So it's kind of a funny theory to have turned out to be the true one, right? It's not one that you probably would have guessed. You might have guessed some nice closed cosmology where it was going to recollapse to a big crunch, right? Big crunch, big bang, big crunch. Symmetry, it's the kind of thing you might have guessed at, but it doesn't seem to be the case. This theory also does nothing to explain the initial conditions of the universe. And so I'm going to say, what are they? I'll come back to that. Let's just for a moment mention inflation again. So here we are again. This is another kind of schematic of the universe. Here we are in the present day, 14 billion years. Here's where the microwave background comes to us from, at this point where the universe makes the plasma to neutral transition at 380,000 years. But this is a very logarithmic time scale now. So now we're going back in time 3 minutes. It's only, it's a big increment. Nuclear fusion occurs at a few minutes, right? That's when the nuclei of the atoms are formed. And then as you go back in time to kind of microsecond time scales, these are energy scales, these are temperatures which we can recreate on Earth in particle accelerators, but they're very, very high temperatures, kind of billion-degree temperatures. Now we can trace, using particle accelerators, the physics of how matter behaves all the way back to a very early time, about a nanosecond or something. Now, inflation is a proposal for what happened at 10 to the minus 32 seconds. Now, what the hell is that, right? So that's 0.00032 times 1 of a second, right? So a billion, I don't know what, right? Some tiny, unimaginably small fraction of a second. Now, the idea is that inflation occurred at this time, at this very high energy scale. And what it does, as I'll explain in a moment, is it solves the so-called horizon and flatness problems. It was put forward by these guys, Alan Guth and then André Linde. They were very famous for it. I tried to find pictures of them when they were young, but I didn't really succeed. So they were much younger than this when they came up with this theory. Now, what this theory posits is that the universe at this very, very early time underwent a period of exponential expansion. So I just got through telling you about how in the future the universe is going to expand exponentially at an ever-increasing rate. But we believe that it did, or at least the theory of inflation posits that it already did that one time, very, very close to the beginning. And it expanded by a vast factor in a tiny fraction of a second. And what it did was it took a quantum fluctuation in some pre-existing space, and these theories say nothing as to what that pre-existing space was, but it says that quantum fluctuation was blown up almost instantaneously to a size vastly larger than the entire observable universe today. So what is the horizon problem? So here we are at Earth. We're receiving light from 2 points on this microwave background sphere that I showed you that are diametrically opposed, 180 degrees apart. And we see almost equal brightness in both directions, right? I showed you the ripples in the brightness, but the overall glow is almost exactly the same. Now, that light has only had time to reach us here in the middle of Earth today, right? Those two regions of space are what we call causally unconnected. They've had no ability to communicate over the lifetime of the universe thus far. And so how the hell do they know to be at exactly the same temperature? So what inflation says is, well, they were once in causal contact at this in this quantum fluctuation at this very early time. And then inflation blew them up effectively superluminally, effectively faster than light, and put them out of causal contact, and they're just trying to reconnect today, right? So it explains the so-called horizon problem, how it is that regions of space that shouldn't know anything about each other apparently do. Now, it also solves the so-called flatness problem. Now, remember I told you in general relativity, space can have any curvature, either positive or negative. And zero curvature, where parallel lines truly are parallel forever, is a very special case. It seems to be the universe that we live in, which is great because you don't need to throw out your high school geometry, right? It's still applicable. Parallel lines really are parallel. But it's a very special case, and it demands explanation as to why it would be like that. So what inflation says is, imagine I'm a little stick man and I live on this sphere. And then I take that sphere and I expand it by some vast factor over here. And then I examine it on a relatively local scale. And when I say local scale, I mean our entire observable universe is a local scale for the purposes of this discussion. If I examine it on such a scale, then it appears to be very flat, right? So if I blow up the sphere enough, its surface looks flat when I examine it close up, so to speak. So inflation naturally solves the so-called flatness problem. It makes space flat by hyper-expanding it. Okay, so it's a nice idea, right? And these guys got famous for it. And theorists love it, by the way, because it seems like it very naturally explains the initial conditions which seem to pertain, right? So when we look at that microwave background glow, we can get a lot of information out of it. And one of the things we can get out of it is what was the conditions like statistically at a very early time. And this theory naturally sets up the universe like that, right? So can we get any direct evidence that it happens? Well, one way to ask a question when you have a new theory is to ask, to try and test a theory that you have is, well, what predictions does it make that I didn't already know when I made up the theory, right? Because otherwise you may have made up the theory to fit those things that you already knew, right? So it makes an additional prediction. It says that there should be a background of gravitational waves in the universe. So let's go back to this diagram. Inflation is occurring here at this very early time. It injects into the fabric of space-time fluctuations, perturbations, blobs, if you like, right? And it injects them both in terms of density blobs. Those are the ones that go on, they propagate all the way down to the present day. They are the seeds of the structure that we see around us in the universe today. They are the seeds which grew into galaxies and clusters of galaxies. But it will also naturally inject, its inflation process naturally injects into space-time gravitational fluctuations, which will be manifested as gravitational waves. So these are fluctuations in the fabric of space itself which propagate through space at the speed of light. Now, we confidently believe that such gravitational waves exist. We haven't actually detected any. There are experiments right here on Earth trying to detect them in the present day, not actually from the Big Bang, but from things like merging neutron stars in our relatively nearby universe. So any year now, they will be detected. We confidently believe they exist. Now, what we're trying to find out is did they actually, can we see evidence for the ones that come from inflation, right? So those perturbations, fluctuations are injected into the universe. They travel down to the present day. They are present here today, although it would require a detector kind of on the scale of the solar system to detect them. There are actually plans for decades in the future to build such a thing. But what we're trying to do is we're trying to see the imprint of those gravitational waves in the cosmic microwave background pattern. So we are essentially a remote sensing gravity wave experiment. We're trying to look for a particular imprint. Okay, so this is just to emphasize that the universe to us before 380,000 years is dark, right? We can't see through it because it's opaque. But we can, the gravity waves pass through it no problem, and they potentially write into the pattern of the microwave background, into the polarization pattern of the microwave background, a particular signature, a particular swirliness into that polarization pattern. So I haven't talked about the cosmic microwave background being polarized, okay? It is to a small degree. That polarization comes in two flavors, and I'm not going to try and explain what these two flavors are. Basically, they're a swirliness and an unswirliness, right? The swirliness is called B modes. That's the thing that can be made by gravity waves, and mostly only by gravity waves. And then E modes are kind of vanilla form of polarization, which we expect to be there, and in fact we've measured it. Experiments that I've worked on myself over the last years, we've measured it very well. So what we're after is to measure this so-called parameter r. So all r is it's just a number representing the amount of gravitational waves, right? And this diagram is, again, the same kind of diagram that we've already seen. It's like a lump sorter, right? So this is the size of the B modes from large to small, reversed again. And this is the amount of B modes from less to more. The colored points that you're seeing here are all little down arrows. And so until recently, all we had was so-called upper limits. Experiments had measured the sky, and they'd said, if there is a B mode, it's no bigger than X, right? And so then you can draw a line on the plot with a little down arrow saying that whatever is real is less than those symbols. Now, on the diagram is also drawn here the so-called lensing B mode. So I said that only gravity waves make B modes, but that's not quite true. There's another effect that can make them, but mostly at smaller angular scales, right? Mostly at smaller structures on the sky. And then here are some theory curves, these dashed lines, for different amounts of gravitational waves, different values of this R parameter. And so you can see these experiments had measured the amount of gravitational waves, and they'd proven that it was smaller than. So you're proving that R is smaller than, right? It's definitely smaller than 1, right, was the previous result. Okay, so that was the situation at the beginning of this year. So now I'm going to talk about our current experiment, which has been very much in the news. Some of you will have heard about it. And I'm going to talk, here's a picture of the collaboration, the guys who made this possible. So it's a collaboration. Now these CMB polarization experiments have reached kind of, 30-person scale, right? So it's a mid-sized collaboration. Some science experiments are huge now, right? When you hear about the LHC, these are like 1,000-person or multi-1,000-person collaborations. We're still pretty small, but bigger than it used to be. It used to be like one professor and his grad student on the roof of the physics building a few years ago, right? It's grown from that scale. So it's 4 main institutions. There's John Kovac, the leader at Harvard, Xiaolin Kuo, the leader at Stanford, Jamie Bock, the leader at Caltech, and myself here at University of Minnesota. Big crew of grad students and postdocs, and a number of supporting institutions that mainly provide critical pieces of technology, specialized technology that we use. Okay, so now I'm going to digress a little bit. This is the kind of easy part of the talk. So I'm going to talk about the process of going to the South Pole, how we do that, and what it's like, right? So we travel by commercial aircraft to the west coast, and then by commercial aircraft to New Zealand, to a city called Christchurch on the South Island of New Zealand. Then the US military flies us down there, the US Air Force flies us down to a base on the coast of Antarctica, which is called McMurdo Station. And then the New York Air National Guard fly us up to the South Pole proper on the high plateau of Antarctica. So that's the process of actually getting there. I don't know how many of you are aware, but Antarctica is really big, right? It's larger than the entire US, and the ice sheet is up to 2 miles thick. If it were to melt, which, that would be really bad. Hopefully that won't happen. If it were to melt, there would be big mountains exposed, and the location of the South Pole, it would actually be kind of roughly sea level. So the ice there is about 10,000 feet thick. McMurdo's down here on the coast. That's the southernmost point, or one of the southernmost points that you can get a ship to. So that's why the support station is there. So this is all of the work that we do that I'm going to describe at the South Pole takes place under the umbrella of the US Antarctic Program, which is run by the National Science Foundation. So a huge thanks to them for making this possible. They operate in Christchurch, New Zealand, a clothing warehouse, which in proper military terminology is called the CDC, the Clothing Distribution Center. And when you're an official part of the program, you show up at the CDC and you check in. It's kind of like, it's checking in for military service, essentially. You give up your civilian freedom at this point, and you're issued with a full set of clothing. It's awesome. You walk into this building and you walk out 5 minutes later, a fully equipped Antarctic explorer. No need to research clothing or any of that stuff that private expeditions have to do. It's all laid on. You get a lecture about it. Then they issue you with your stuff, and they've got lots of it. And I really wish I had some of this clothing. Every time I come back here to Minnesota, I'm really tempted to just keep the bags, right? But it's worth thousands of dollars. They won't let you keep it. I should buy some. I mean, it's awesome. It's so good that if you wear your clothing, even though it's way colder at South Pole than it is here, So like the coldest day here is like the warmest day there, right? Negative 30 F is a typical summertime temperature down there. During the winter, the temperature plummets to about negative 120, right? So this is temperatures that are outside the comprehension even of a Minnesotan. But if you wear your gear, certainly during the summertime, you'll be just fine, right? So then we fly down to McMurdo. Here's a picture of me having just come out of this C-17 aircraft on the ice at McMurdo, or near to McMurdo. McMurdo is this supply base on the coast. It is a kind of grungy place. There's huge oil storage drums. There's a large base. It's a big cargo yard, right? This is a logistics base for the entire U.S. Antarctic Program. And it's kind of what I imagine a mining town in Alaska would be like, right? It's kind of populated by the same kind of people as well, I think. From there, we fly on up to the South Pole proper, over the Transantarctic Mountains, and these are like 10,000-foot mountains buried in the ice, right? Just peeking up above the ice. You fly up over those to the high plateau. So there's no means to get any scale in Antarctica, right? I mean, you're looking at this picture and it doesn't look that impressive, but these are massive mountains and huge glaciers. Here is one of the LC-130 aircraft. So these are Hercules, four-propeller, kind of 1950s technology military aircraft. They fly us up to pole, and these are serious heavy-lift aircraft. They are the only heavy-lift aircraft in the world that have skis, and there's no proper runway at the pole, so they need these ski-equipped aircraft to land. And you can see a big chunk of one of our telescopes being dragged out of the back of the belly of this Hercules by a big earth mover here. So really good logistical support, right? They can bring 20,000-pound objects to pole for us. Here is the obligatory picture of me at the actual South Pole. The South Pole is an ice sheet, right? The Antarctic ice sheet is flowing at the rate of about 30 feet per year. So each year they have to replant the South Pole, and so there's a string of them stretching out across the ice sheet. It's a really sweet gig. Some guys from the USGS come down. They used to have to make elaborate measurements on the sun. It took them several days to really locate the South Pole accurately. Now they just come down with a GPS receiver. They have breakfast, they step outside, they say it's here, stick the pole in, and they go home. Now the thing to appreciate about the pole is just the incredible flatness and barrenness of the landscape there. It's like being on a frozen ocean, right? It's completely flat to the horizon, just looks like a circle around you. It's just flat snow in every direction. The nearest piece of rock sticking out of the snow is like 300 miles from this location, right? There is nothing there. There's nothing living, only the humans and the small amount of cargo that they've managed to bring, right? I mean, it's a lot of stuff, but when you walk away from the base, it's nothing, right? It's just a little speck on the whiteness. All right, so why the hell do we do this? Why do we go to the pole, right? So we do it primarily because the atmosphere there is super dry. It's very counterintuitive. You get off the plane, you're standing on 2 miles thick of ice, but yet the meteorologists tell you that it's a hyper desert, right? And the reason for that is that the ice has been accumulating for millions of years. That's part of it. And part of it is it flows in from elsewhere. It's a glacier, right? So at that actual location, the atmosphere is fantastically dry. We're on the Earth's rotational axis. That gives us this 1 day-night cycle per year that I was speaking about. And the long night makes for a really good period of data taking, right? There's no annoying sun emitting microwaves getting in our way. It sets, it stays down, and the sky gets really dry and really clear, and we can see out into space and see the microwave background that we're after. There's really excellent support infrastructure. There's power, as I just showed. There's cargo capability. There's data communications via satellite to get our data out. There's food and accommodation provided, and there's even extremely limited entertainment. So great place to operate. So I just want to re-emphasize the crew of postdocs and graduate students that make an experiment like ours possible. And I also want to make a special shout out to the winter rover, the guy who stays with the telescope through the long night, keeping it running while it takes the best data. And so for Bicep2, it was Stefan Richter in 2010. In 2011, it was Stefan Richter. And in 2012, it was a guy called Stefan Richter. So this guy did 3 back-to-back winters, right? Which doesn't mean he was there for 3 years straight. He gets to leave for about 2.5 months in the summer. He gets well paid. He has no expenses while he's down there, so he can go anywhere in the world and do anything he would like to do. But then he has to come back to man the telescope through another winter. And we are really fortunate to have these individuals that we've managed to find who can stay sane through this process, right? Stefan, although he's shown here smiling, he copes with it in the manner of being grumpy all the time and not getting any grumpier. Right? We've got another guy who does it by being happy all the time, but they can do it. They have a special mental capability to survive, and not only to survive, but to remain functional and professional and on the case through the long winter. Okay, so a few words about the technology behind our telescopes. So it's a succession of telescopes. There's Bicep2, which was the successor to Bicep1, which ran a bit earlier. The currently running experiment is Keck array, and just on its way to pole right now is Bicep3. Now, what these telescopes do is they're just a relentless scaling up of the number of detectors, of the amount of sensitivity, right? So these are small, compact telescopes. In the focal plane, this focal plane here is shown, it's about a foot across, right? This is about the size of an LP record, for those of you old enough to remember those. The little colored dots here represent the pixels, the detectors, essentially the little reception spots on the sky that the telescope is collecting radiation from. So Bicep2 scaled up from Bicep1. It used this new flat focal plane technology, which is mass reproducible. And so for Keck array, you just take that and multiply the same concept by 5 and just have 5 of them. Bicep3 takes that and then puts all of those into a single focal plane, and then the logical extension would be to build an array of those, right? So this is just a constant scale up in terms of sensitivity to get down to the levels that are interesting scientifically. So the Bicep telescopes are very simple. It's just the same as a backyard telescope. It's got 2 lenses, an objective and an eyepiece lens. That's that focal plane I was just showing you a picture of down here. So the light is funneled down. The microwaves come in from the cosmos. They're focused down onto the focal plane. You can see a diagram of the focusing going on here. And each of those pixels in the focal plane, each of those detectors is sensitive to radiation coming from a little spot on the sky. Okay? This whole thing's about 4 feet long, 5 feet long, a couple of feet across. It's housed inside a vacuum vessel, and it needs to be housed inside a vacuum vessel because it's cooled to 1/4 Kelvin above absolute zero. We need to cool it that much to get the lowest possible noise performance out of the detectors, to get the highest sensitivity to that radiation from the cosmos. So just to zoom in, here's the focal plane again. It's got 4 tiles. This is about 4 inches by 4 inches. Zooming in on one of the tiles, you can see that it's an 8 by 8 array of pixels. Zooming in on one of the pixels, you can see that each pixel is a 12 by 12 array of little antennas, little slot antennas. So each of these is a couple of millimeters long, and those are the things that are actually picking up the radiation, picking up the microwaves. That radiation is then summed up in a summing tree, which you can see it's kind of like lines on a circuit board almost. And the radiation is piped down into a thermally isolated island, so an island that's supported by very skinny legs, whose temperature is then raised by the radiation coming in and then converted back into heat in a resistor here. And then there's a thing called a transition edge sensor, which is a super sensitive thermometer, which measures the temperature of that little island. And so the net result of this is that as you take the telescope and you scan it around in the sky, each of those little reception spots is moving, and so it's going from places where the sky is hotter to colder and hotter to colder. And the temperature of this island actually tracks, the actual physical temperature of the little island tracks the temperature of the radiation coming in, the intensity of the radiation coming in, and then we get to read it out as a voltage. So it's very, very simple concept. The telescope scans around. It's a little movie. It's a movie taken during the daytime now. You can see it scanning backwards and forwards, left and right on the sky, speeded up by about a factor of 60. Scanning backwards and forwards, making a raster map of the sky. Then it does little dip moves, little calibration moves, and then it goes back to scanning at a slightly different elevation. So we make a kind of like an old-style TV, raster scanning TV pattern. We make a raster map of the sky. So here are the maps. On the left here, the so-called the signal maps, where we just add up all of the data together. On the right here is a so-called jackknife map, where you deliberately cancel out the sky signal. This is looking for jackknives. It's a little too technical for this audience, but just to let you know that we do that test. So this is now a movie that integrates down. So what we're doing here is we're making maps and we're adding in more and more data over a 3-year time scale, 2010, 2011, 2012. As we add in more data, the signal maps on the left here converge to a particular structure. That is the actual polarization structure of the sky. Whereas on the right, the jackknife maps just keep getting cleaner and cleaner as we average down the noise. So that's the basic map-making procedure. So let's express those maps as little polarization pseudo-vectors, right? So I haven't talked about polarization or how the microwave background gets polarized. I'm sorry, I don't have time. But you can express polarization. It's a property of light that has a direction, right? And so you can draw a little arrow on the sky that shows the size and the direction of the polarization at that particular point on the sky. This is just a map of a chunk of the sky, right? A little box on the sky. Now, this is the total polarization signal. So now let's extract the B-mode contribution to that, right? So you've got this pattern of polarization. Now let's look for the swirliness in it, which is going to be the signature of gravitational waves. Well, first of all, you can see that there's very little, right? So most of the polarization that we measure is not the thing that we're after. It's not the magical B-mode that we're after. Now, if we blow up the scale of this diagram by a factor of 6, then you can see the swirliness, right? So this is a real B-mode that we've detected on the sky, the first time it's ever been done. Now, you can say, okay, well, that's just a swirly pattern. How do we know it's real? And that's a very good question, right? So in order to know that it's real, we have to do simulations of the whole experimental process, very computer-intensive simulations. And in the top panel here, we're seeing the real signal again. And the lower panel is a simulation where what we put in was just the vanilla model, so the no gravity wave model, and instrumental noise. And you can see there's way more structure in the upper panel than in the lower, and that is demonstration that we're really seeing real B-mode on the sky. Right? So now let's plot that again in this form where we have the amount of the size of B-modes on the x-axis going from larger to smaller, and the amount of B-modes on the y-axis going from less to more. The black points are the real data, right? So that's the data that we've measured. That's the histogram of B-modes on the sky. The solid red line is the vanilla model. That's what we would expect to get. We would expect to get points that scattered around that solid red line if that was all there was, if there was no gravity wave contribution. The upper dashed line here is what we would expect to get if there was gravity waves plus that vanilla model that we expect to be there. And you can see that the black points look like they agree with the dashed line much better than they agree with the solid line. In fact, the chance to get the black points, if in fact the red solid line is reality, is about 1 in 10 million. Right? So this is a very high, so-called high significance detection of gravitational waves. Well, sorry, I should rephrase that. It's a high significance detection of something other than the vanilla model. All right, so what is it, right? Is it really the thing we're after, or could it be something else? So the number one thing, something else that it could be, is experimental systematics. But we think we've ruled that out, right? We've done all of these jackknife tests, and we're very confident that it's not experimental systematics. So could it be so-called foreground contamination from our galaxy? So remember, we're in a galaxy, and we're trying to look at way out into intergalactic space, but the galaxy is between us and that. And so it can also emit and put radiation into our telescopes, which could confuse us. Right? So the first thing we do is we just pick a patch of sky which is known to be very low in terms of galactic emission. Our galaxy is a disk-shaped structure, right? So if you just look up or down out of the disk, you can find areas of sky where you've nearly got a clean sightline into intergalactic space. But no sightline is completely clean. Now, this is a slightly different diagram than the one that I've been showing you. So this is the amount of contamination on the y-axis. This is frequency at which you're observing, right? So we can tune our telescopes to any frequency, to any color, as it were, of microwaves. We choose to tune to about 150 gigahertz. That's because at lower frequencies, going down in frequencies to like 10 gigahertz, for instance, there's very strong synchrotron emission. So what is synchrotron? Well, it's high-energy electrons spiraling in the magnetic field of our galaxy, and they emit very annoyingly radio waves, right? So at low frequencies, the sky is glowing with synchrotron radiation from our galaxy. At high frequencies, it's glowing with thermal emission from dust grains. Our galaxy is full of dust grains. They're actually critical to the formation of stars. We wouldn't exist if there were no dust grains in our galaxy. But again, they're very annoying to CMB scientists like myself because they emit. And they emit a certain amount of polarized radiation. And so at high frequencies, that's the dominant effect. So this is a projection that was made before our experiments saying that the sweetest spot would be at around 150 gigahertz. And the emission there, the contamination there, would be very low. It would be small. It would be much smaller than the size of the signal that we seem to have seen. So that was the situation at the beginning of this year when we were, studying our data. We'd been working on our data for like 2 years, right? Convincing ourselves that the signal was real and not some artifact of our experimental system. But then the question arises is, how much dust contamination will there be? So we ran a bunch of models that already existed, and we got these projections for how much of these data points we could explain through dust. This is the standard plot again, amount of B modes, size of B modes, and these lines represent the output from these various pre-existing models. And you can see it's like a tenth of what we had measured, right? So we were pretty confident that, what we were seeing was gravitational waves and not dust. Now, nobody really knew, right? These were projections, these models. They're not our models. Other astrophysicists have made these models. But nobody really knew the true level of polarized dust emission except the Planck space mission. So that finished a couple of years ago, but they were still sitting on the data, right? Because, it takes a long time to analyze this data. It's really hard. We struggled with our own data for years. They were struggling with theirs. Now, here's a picture of this Planck space mission in some very dramatic artist rendering. Okay, so that was the conclusion around March of this year. We'd measured these points. We'd gone from having only upper limits to having actual detections of B modes at 150 gigahertz at this sweet spot frequency. It really did look like the gravitational wave signal that we were after, but there was still uncertainty about the galactic polarized dust emission. Okay, so, cautiously or incautiously, we held a press conference. It generated tremendous amounts of interest from around the world and in the global media. I was actually kind of surprised at the reaction of the global media because, we're talking about 10 to the minus 32 seconds. It's super exotic stuff, right? It's the tiny fraction of a second after the Big Bang. I wasn't sure that the global media was going to pick up on it, but they did in a really big way. Here's some, front pages of various newspapers. Funnily enough, USA Today had the best graphic, right? The Financial Times put up a picture of a pretty galaxy that's got absolutely nothing to do with our work. I was on the TV in the UK. There was a lot of. It was on Fox News. It was ridiculous, right? I mean, that was really difficult. That one. Anyway, so there was a storm of attention from the media and the science community. I expected that. There were many queries about, basically, had we screwed it up, right? Was the signal real, or was it just experimental systematics? As I've emphasized really hard to get to these sensitivity levels, and there was a lot of concern that it might just be false signal. That's mostly gone away. I think virtually all of our peers are convinced that the signal is real. There were concerns about synchrotron emission. They've also faded away. That doesn't seem to be a valid concern. But there were persistent concerns about dust. And most of these were based on analysis of PDF files. Because the Planck guys, although they hadn't released their data, they'd given talks, and then they'd posted the talks online. And so you could download the PDF file and try and extract the data from the plot, right? Ridiculous, right? Really not very good science at all. I have to admit that we did a bit of that ourselves. We probably shouldn't have done. Other people did it a lot. Anyway, as of 19th of September, we finally actually have some solid information from the Planck guys. And it does kind of look like polarized dust emission is much stronger than people had previously projected it to be. And possibly it explains all of the signal that we've seen, right? So it's a bummer, right? For everybody. I think, everybody, certainly all of the scientists would be delighted, would be very excited if this were true. It remains unclear, right? So we are doing a joint analysis with the Planck guys right now. In fact, they're coming here next week to the University of Minnesota to discuss. And we're trying to, together they're better than the sum of the parts, as it were, right? So the way to analyze this data in the most productive manner is to do a joint analysis, and that's what we're doing. You can also get at whether or not the signal is cosmological or whether it's dust by making measurements at different frequencies. That's, of course, what the Planck guys have done at much higher frequencies. You can also go lower, and we've done that ourselves with our own next generation experiment that's running right now. It's just finishing up data taking actually just this week, and there's guys in the audience who are gearing up to analyze that data as fast as possible. As I mentioned, Bicep2 is right now on its way to pole, which will also have a powerful role to play in disentangling this puzzle. So basically the message right now is to stay tuned, right? It remains unclear as to whether we've discovered what we thought we had or whether it's actually just galactic dust emission. So the kind of final thought that I want to leave you with, so just stepping back from our own experiment, is just the realization that the amount that we've discovered about the universe using the microwave background and using various other kinds of cosmological measurements is just astounding, right? It's really quite amazing that we understand the universe right back to a tiny fraction of a second. We know how old it is. We know how much stuff it's got in it of the various different kinds. We know all sorts of things about the fabric, the structure, and the nature of the entire universe. And it's really quite amazing that, A, that information is available to us, like flowing into the solar system, and B, that we've evolved from apes on the African plains to being able to build instruments that can record that information and disentangle it and understand it. It's just an astonishing feat of modern science, and I'm really proud to be a part of it. So thank you very much for your attention.
Bicep2 was built where?
Bicep2, the cryostat, was built and integrated at Stanford University, and it's just been completing testing at Harvard. We built some parts of it here, so when it's complete at pole, it'll have some University of Minnesota parts. It's not been a big emphasis, so we kind of share the work around. Keck was large parts of it were built here.
I was just wondering also to Bicep2, you showed the sensor arrays, and the one for Bicep2 was asymmetric in contrast to all others. Is there a reason for this?
Yeah, I mean, it's a boring technical reason. So packing the tiles into the focal plane, you would naturally have two more, as you noticed. And it's because the readout electronics comes in discrete units. And so you'd have to have a whole other crate of readout electronics to instrument those last two spots in the focal plane, and it wasn't considered worthwhile. It's really hard to get enough electronics onto the cryostat as it is.
What is the current level of funding per year, and how has that changed from one to the next stage?
So are you asking about, so the question is about the level of funding. Are you asking about our experiment or all of the CMB experiments? Okay, so I would say that our entire program thus far, Bicep1, Bicep2, Keck, we're talking, and it's hard to account properly, but we're talking somewhere between $10 and $20 million, probably towards the upper end of that range. Now, some of that money comes from the National Science Foundation. Some of it's come from the Keck. It's a private foundation, which hence the name Keck. Some of it comes from NASA through JPL, where the detectors are made. So it's a complicated mishmash. Some of it comes from universities. So our annual budget is maybe a couple of million, and the total amount of money we've consumed with this series of projects maybe 15, pushing 20. That may sound like a lot. It's incredibly cheap, right? The LHC is like $1 billion, billions of dollars. The Planck space mission that I mentioned is $1 billion experiment, right? So we're actually small fry in the mix. Okay, so the question is, does the CMB pattern change with time? And of course, in principle, it does, right? Because we're seeing the light from the spherical shell, and as time passes, we're seeing light that came from progressively further away. And so we would be probing the structure of the universe on a different shell. and so it would change. Unfortunately, the timescales are like billion-year timescales, because whilst the thickness of that shell is probably only 30,000 years at emission time, that gets time dilated by the expansion of the universe. So incredibly hard to detect any change. Maybe with futuristic degrees of sensitivity, you could detect tiny changes due to time evolution over human lifespan, but very hard to do and not a great deal of point, I think. We would have to wait a billion years to get really fresh information.
There's got to be a frequency whereby the dust noise is probably minimized and the microwave natural cosmic background is maximized. Is that the reason why you were trying to focus around 100 down from 150, or the data from a Planck led you to that direction?
So the question is, what is the absolute best sweet spot frequency? And is 150 it? So it actually depends on what fraction of sky you're trying to measure. This diagram, since you asked, this diagram shows curves for both the full sky and for decreasingly small fractions of sky, and then this bottom one is supposed to be for the very best little bit, right? And so you can see that because the dust emission is more concentrated in the plane of the galaxy and the synchrotron emission is more extended, as you go to larger sky regions, the sweet spot's frequency shifts down a bit where you want to be. The reason that we're shifting from 150 down to 100 is not specifically guided by Planck, right? So this instrumentation was in the pipeline years ago before we had that data. We've only just gotten that data. It probably the new information from Planck would push you down a little bit, since the dust emission is stronger than expected. It basically shifts these lines up, and it shifts the crossing point between the rising and falling curves a bit lower. But really, you just want two frequencies, you want multiple frequencies, and you want them to span the sweet spot range, right? Because you're going to need more than one frequency to disentangle the dust from the cosmological signal. We thought we could get away with one, right? And it turns out that, unfortunately, the galaxy doesn't seem to allow that.
It was clear from the graphics to me why the wavelength would be stretched with the expansion of space, but why was the amplitude not also increased? At least with the graphics, the amplitude for the examples was the same. Or is that just a limitation of the graphics? Or demonstrating I did not do well in physics in high school.
Okay, so the question is that the wave chain is stretched both in wavelength, but why isn't the amplitude increased? That's a very good question, and I think it kind of... the problem is it leads to the breakdown of these analogies, right? So you can make these pictures, to try and communicate these ideas, but really a photon is a quantum mechanical oscillation, and so the stretching it's kind of an analogy. Actually, the energy density is diluted, right, by the expansion, because you're taking a given amount of photon energy that you've got in some piece of space, and you're stretching the space. You're diluting that energy away, right? So actually, the energy density goes down as the fourth power of the expansion. And one of them is the stretching of the photons, because longer wavelength photons have less energy than shorter wavelength photons. So it's actually the opposite of what you say. The amplitude effectively goes down, right?
So what would you do if you had $1 billion to study these kinds of issues?
Wow. So the question is, what would I do if I had $1 billion to do these kind of experiments? And that's a great question, and one that I'd never really thought about, because we have a tough time getting hold of the amounts of money that we need to do these relatively small-scale experiments. So what would be the ultimate? So people are talking, of course, about a next-generation space mission, right? So Planck is a great experiment. It's going to deliver a lot, but actually it doesn't look like it's quite the ultimate, right? You could do a better version. You could make it more sensitive. It's not unlimitedly sensitive, which is why we can beat it, essentially, on the ground with our little telescope. So you could just make a way more sensitive version of Planck, and there's talk about doing that. Whether it will be possible to get the momentum that's required to generate, $1 billion to get a space mission approved is not clear. We are also, as a field, so the CMB experiments have been growing, so they've also been merging, right? The size of the collaborations has been growing, and the number of individual experiments has been decreasing. Some would argue not as fast as it should have been, but it's been decreasing. And the ground-based community is headed towards something called CMB S4. Stage 4, right? Rather unimaginatively it stands for. And this will be, a considerably larger, order $100 million project, and there'll just be one of it, right? And that will have higher angular resolution than our telescope, because we've deliberately gone for just a single issue of the gravity waves. But there's other science to be done if you have slightly bigger telescopes, and way more sensitivity. So basically, what would I do if I had that $1 billion? I would build way more detectors, so way more sensitivity. I would spread it not just across the small aperture telescopes like we've got, but also some bigger ones. And I would diversify the frequencies as much as possible. There's a limit to how much you can diversify the frequencies on the ground, because the atmosphere is only transparent at certain wavebands. And so there's a window at 100, at 150 where we currently operate, at 220. You can't really go any higher than 220, and you can go down. You can also do balloon experiments, which is a kind of halfway house between ground and space, and from there you could access higher frequencies. So I would do a mix of all of these things. So basically just what's happening now, but more of it.
Okay, first of all, again, I would like to thank all of you for coming tonight. Too high. Better? Okay. Thank you all for coming tonight. This has been great to see you all have this opportunity. The overview will be that you can go through those back doors to your left, and then you'll find this Eyes on the Universe exhibit. But before you go, I want to just close. Clem mentioned that in the future, gravitational waves will be detected. And I promise you, when they are, we'll have a public lecture here on that from somebody at the University of Minnesota that's involved with that. And the last thing is that in your program, you've seen if you would like to participate in furthering our mission in terms of public outreach, there's a way to do that. In fact, I'm now looking for a sponsor for our next Kaufmannis lecture, and if you'd like to contact me about that, that would be also great. But once again, thank you so much for coming, and let's take this last opportunity to thank Clem on this wonderful lecture.